Well, welcome to the back to the podcast. As you can see, if you're watching on YouTube, we have a panel discussion today, but it's a bunch of heavy hitters. The rock stars of metrology are here. We got Dilip Shah, Greg Cenker, and Henry Zumbrun. Going to talk about their very popular paper that's in development stage right now, but you guys have put it out for feedback. And I did a thumbs up on that post, and I have seen a lot of people asking for it. So it's definitely been popular. So welcome to all three of you.
Glad to be here.
Thank you,
Now, Henry, since you're the official co-host, do you mind launching things off? This is going to be one where I'm more sitting back and I'll ask questions as I have, but I think it's important that you guys talk about this document, especially for those of you that don't know, Sign Calibration Schools will be having a public general metrology course. And so decision rules is very important in there. We're going to be talking about that even at level 1, because I know many of you out there are being sent out to customers' locations to do things, even as a beginner, on your own in an island. So you need to know about decision rules. You need to know about how to communicate with your customers. So Henry, without further ado,
Ryan.
Do you want to kick this off?
Yeah, absolutely. So everyone that's out there, we've had guests on and interviews with guests this season, and this one is just a specific topic discussion that's near and dear to all of us and should be near to dear to all of you that are having anything calibrated. You want to know, many people want to know if your item passes or fails calibration. Some people may even want to know if it's an indeterminate pass or an indeterminate fail, or some of the other things, but it's generally binary, meaning either my item's good or it's bad. I want to use it for another year. As we get up to the higher echelons of the pyramid, or the NMI level and the primary levels, like we are Morehouse, we don't care so much anymore on the pass fail. We just want really, really small measurement uncertainties, and then we'll do our own analysis and figure it out. Though there still are some items we use if we want to do temperature in record temperature in our laboratory. We claim like a barnyard spec of we're monitoring to within 0.2, and we have devices that are much like O2, and on those devices we send to our provider and say, hey, please calibrate to 0.05 degrees C. That's the fail if it's higher than 0.5. So that's a decision rule there, though that is more of a barn door approach. And joining for this discussion, the three of us wrote this document. Greg Cenker with IndySoft and Dilip Shah from the planet Mars is here. So it's nice that he made it the whole way here. Those that do not know, Dilip and I have a banner that goes back and forth, and all of us will try to keep this a little bit more lively. But yeah, I would just asking different people questions, starting with Dilip. And what Dilip consults, so does Greg. And what do you see when you go out there, Dilip, regarding decision rules? And
so decision rules, everybody thinks it is more current with the release of the 2017 revision of ISO IEC 17025 standard. But it was there in the previous revision of the standard, which was the 2005 revision of the standard. But in there was just a one-sentence requirement, which basically says if you make statements of compliance, the uncertainty of measurement shall be taken into account. And
5.10, Dilip?
5.10.4.2. So that was part of that. And it was one sentence, and there was other things in that subsection or subclause that I mentioned. And before that, when you think about that, so it is not a new topic, but with the new 1725, the 2017 revision to the standard, they had a whole subclause related to that. And the accrediting bodies started, enforcing and, assessing heavily to that. And as anything, it causes a heartburn in the calibration and testing community, the calibration and testing labs that are accredited to 17025. But it has been around, the topic has been around, and if we look even further in basic quality assurance statistics, the concept of process capability index, that has its roots in kind of part of the decision rule and so on. And if you look at the process capability index, it basically just minimizes the risk by providing a proper process capability index of 1.33 or higher. So I just wanted to give a little bit of background in there. And when in our metrology community, when things are confusing and so on, it is always nice to have a document. And I believe in this KISS principle, which I call keep it simple, smart. And I think this was fun working on this document to make it, keep it simple, smart concept.
I would have thought you meant KISS like the band, Knights in Satan's Service. No? No.
Well, maybe that
Greg?
too.
No.
So Greg, what do you see in industry? Because Dilip hit on the background of decision rules and that they were in the ISO IC 17025 2005 standard. Though when we go into industry, it's not keep it simple, smart, is it?
No, it's not. Matter of fact, from what I've seen in industry, is unfortunately a lot of times because they're not taking the risk and the uncertainties into account with regard to some of their process standards. They assume that because they have a relatively stable CPK process, that doesn't necessarily mean that that's the best that they can do. When you start drilling into things a bit further, what I've found is, unfortunately, I found companies that are making products on equipment that is less accurate than the product that they're trying to manufacture. Case in point, one of my clients was doing that very same thing, and I think I mentioned this on our previous podcast, but I'll keep it brief for now. When they were building these products, they had a specific specification in mind, and when I looked at it, I said, you can't build these products to these specifications utilizing this equipment that you have. Now, keep in mind, they did take data with it, and they asked me, well, what do I suggest in terms of equipment to make their process more reliable and have less scrap? And I made some suggestions, and they didn't go along with the suggestions because they thought the cost of the equipment itself was too expensive. They thought the maintenance was too expensive. So I wasn't reaching them. So I went another avenue and I asked them, what happens when you build these products and they fail the production line? Do you retest them? Do they get reworked? What happens? And I was informed that they simply throw them away. It's scrap. So I asked, well, how much are each one of these products that you make? If it's scrap, what is the cost? And when they told me what the cost was, I did a risk model based on the equipment that they had, based on the specifications that they were trying to do. And I said, okay, just on the face of it, without taking any of your process uncertainties into account, just the equipment wise, you could expect about 27% of everything you make to be a rejection because of your poor uncertainties that you have on your test process. And when I put a dollar amount to it, which was in the millions, then all of a sudden the suggestion to buy more test equipment that was much more accurate, much more reliable, made a whole lot more sense. And to give you an example, if you have a production cost that's $1.3 million, and if you have poor equipment, that testing and retesting can easily, or scrap rate, could be over $2.3 million. So when you take a look at some of the equipment that you might purchase purchase, yes, although it might have a high price, it might be $15,000-$20,000. When you factor that into the runs that you make during a month and how much product that you're actually making, then the products that you reject end up being true rejections, and they're not false rejections. And in this case, for this client, they would have simply been thrown away. So that's the stuff that I've seen, and I've seen it repeated over and over again, where a lot of process managers and managers recall the price of some of the equipment that is necessary to do the process correctly because they think they're saving money up front. Well, they're not. They end up spending more money because, as you know, Dilip, you know certainly just as much as I do, the more that on the assembly line you get, and the further down it gets, and when you discover a problem, the further down it gets, the more money it costs to fix it. If you can go all the way back to the beginning and take that equipment error out of the equation and just get the best equipment that you can that's going to give you the best theoretical process uncertainty, then you can go forward from that. Rest assured that you have a reliable and true process, and that your rejects are going to be truly rejected because it's just a bad product.
Yeah, and just to add to that, Greg, at every stage that you miss, it costs 10 times more to fix it at the next stage, and 10 times more, and so on. So it is an exponential issue, which a lot of times when you are, doing that locally at the factory level or at production level or at calibration level, you don't realize the cost. But when you add up all the costs, just like you did in that example you cited here with that one client, it adds up to millions of dollars.
So it truly does. Had another client that were making a different type of a product, and they asked for some advice. And I asked, well, what types of checks and balances do you have along the manufacturing process? How do you know that you have made everything good from point A to point W before final assembly? And the answer I got was, well, if they don't fit a final assembly, we know we have a problem. And my response was, well, you can fix that all along the way, implementing SPC and having actually live CPK as you make these products. You've got check standards that you can use. There's no reason not to be able to do that. I didn't end up formally working and taking them on as a client, but I heard enough from this client and heard what their resources were like. It wasn't going to happen, and it made no sense for me to jump in and try to get things sorted out, because they really weren't interested in which is unfortunate. They weren't interested in the cost of doing the proper equipment steps that they would need along the way to ensure that by the time they did get to their final assembly, their parts actually fit. But you win some, you lose some, I suppose. Some people just aren't going to get it regardless, because they have a mentality that, well, that equipment just costs too much money, we're not going to invest in it, which is really, really penny wise and pound foolish.
Yeah. So spending $20,000 to save $1 million is not an advisable situation.
Right.
And I'm getting to summarize what you've just said. Accountants are not metrologists. Is that a good summary statement for
accountants?
No, accountants are not metrologists. No.
You know my famous saying about accountants. They are bin counters, and that's all they do. They know how to count. And I kind of joke about the reason the PCs have become very popular. A little bit of history on personal computers. Personal computers, when they came out, they evolved. They were basically just toys for nerds like us who played with it.
Speak for yourself.
Well, I proudly profess to be a nerd. But what happened was, when Lotus 123, that was the first commercial spreadsheet program that came out, accountants loved it. And since they had the power to buy stuff because they handle the money, they started buying PCs with Lotus 1, 2, 3. And that's why PCs became more commercially popular and acceptable in the industry. Otherwise, they were realized more as a tool. And I always joke that, yeah, the accountants used a lot of those because they really didn't know how to add and subtract. And that was a really good tool, the spreadsheet tool. And I used to tell that to accountants at my previous place of work, because when we started out, I had the PC in my quality area, and the R&D guys had one. Accountants would come and use mine with Lotus 1 to 3 on it, and I finally told them to go buy their own. So that's my story about accountants. And I mean, I have to give them credit. That's why the PC has become as popular as they are, because they didn't know how to add and subtract. They're going to hate me for that.
No, but everybody out there, this is we kind of touched on this a little bit when Paul Reese was on, and we got to get into more of the decision rules to help people figure those out and discuss it. It's they don't see it. They want to spend the least amount of money on equipment and expect the best performance. It's like,
Right.
The new Bugattis, $9 million. Now, most of us can't afford that unless you're Dilip, and but he spent all his money on this Mars rocket getting back and forth. So no, but you can't afford that. But there are good alternatives out there, great cars. But what I always equate this to is somebody's buying a Yugo and expecting the performance of a Bugatti. But then you send it for calibration. You send it into calibration. CalLab doesn't do it for free. Even if it's internal, they don't do it for free. There's still costs regardless to calibrate this item. And what ends up happening, if it's garbage or junk, it gets on a tighter cal cycle to stay in tolerance, if you even know what intolerance means, which means, again, getting back to our pass or fail scenario. And then you have this higher frequency cal interval, and you're spending much more money than if you would just bought good equipment. And Greg and I have an article coming out in Quality, we'll plug that in Quality Digest, and it's called "The Definition of a Fool is a Drowning Man Who Tries to Keep a Secret, a story on purchasing the wrong equipment and keeping it." And that's in our decision rules document. Greg has done all of the math for those out there listening, and that you're going to want to go get this document. We're going to post it online, post it on LinkedIn. It's going to be on an MH4 site. I think IndieSoft might have, Ryan's going to have it. So there's going to be a lot of outlets here where you can go grab this document, but all the math is in here, like what Greg's talking about with his client, and it's all in there. We've tried to simplify everything because of these documents are so hard to understand for many people that do not have a really strong calculus basis for you. We get into global risk, double integrals, and everything else. So, both of you, let's just talk about where it is with people and how hard it is for people to understand, and what. We went over what a decision rule is. It's a rule by definition that takes measurement uncertainty into account. You make a measurement, you have a tolerance, and somebody's going to say it's good and bad. And if we use a decision rule, we need to take measurement uncertainty into account. There are other exceptions to this that are beyond this simple acceptance, and we are covering some of those in this document as well. We're covering shared risk in the document, Greg, I guess take like some of this math. It's been hidden behind closed doors for years.
So it has been tribal knowledge, and it's been very difficult to get a comprehensive set of code to be able to handle this really difficult math with double integrals and exponents and everything. This document that we're putting out, I have all the code that is in VBA that the users can take the code, they can open up Excel and open up a new Visual Basic module in the background, copy this code verbatim as it is in that document, paste it in. We have instructions in there how to make it work. And all of a sudden, the veil of secrecy is now going to be lifted because everybody will have access to these math tools. That I can say from my personal experience, I've tried to get working examples of how they worked code-wise for years. And it was like pulling teeth. And finally, when I had all the pieces of the puzzle, there's no reason that anyone else should have to struggle with this. So that was part of the impetus to make this document so that other people freely have access to this information that's been siloed in tribal knowledge for decades.
Yeah, and this is just to add my analogy of accountants to computers. Now we have metrologists where this is very difficult. Like Greg said, you had to deal with double integrals and things. But now you could do it with the computational power we have at our desktop. I mean, we could do it in our smartphone if we need to, because you could load a Excel in your smartphone. So kind of bring that analogy of accountants and spreadsheets to metrologists and computers. And that makes us much more, smarter to implement these tools, because all the number crunching is available in the power of the computer, your laptops, and that you have at your disposal.
Yep, and Excel. There's Excel formulas in there. Yep.
Yeah.
Go on, Greg.
And I just want to add too, and part of the reason that these are so difficult is because they offer no closed form solutions. You can't simply rearrange the equation and solve for X. It doesn't work that way. You have to do it via an iterative process to make the risk volumes balance out in order to get the PFAs that you're trying to achieve. And it's an iterative process. And I think in the code that I have, I think that my fuzzy zero is 1e to the minus ninth. In other words, it's going to keep iterating over and over again in that loop until you have an answer that is 1e to the minus ninth in terms of where the error begins, which is more than enough for a percentage that you're looking for. Because what ultimately you're getting a probability of false accept, and you're getting a guard band multiplier that takes your basic test tolerance and multiplies it by some factor to make sure that you're at that 2% risk. So, how accurate does your percentage of your percentage need to be? 1e to the minus ninth is good enough. And I did enough testing to where you can't see it. It doesn't matter. But that's what makes these equations so difficult and so unwieldy.
Yeah, you mentioned some terms, and some listeners out there may not know them, and we'll talk. We can talk about those now, and the people that are in sign school, as Ryan's going to put, I think this topic up for the people that go to sign calibration to view.
Sure.
Our document, the one that we made, you can go read ILAC G8. You can read JCGM 106. You can read ASME B79. I forget in all these other documents. You can read Introduction to Statistics and Metrology, and I encourage everyone to read that book because it simplifies things a lot. Though if you drop right into JCGM 106, it's very difficult to understand. And a lot of these documents are difficult for someone just to pick up and read. And I don't want to say we're at the the super beginner level with this document, but we're at, if you have a little bit of experience level with this document, I think. And that's when we start talking about like PFA and PFR and these terms. I'll pass that one over to Dilip. If Dilip, you want to take what PFA and PFR and risk is for those that are listening that may not know.
Yeah, so PFA is basically probability of false accept, meaning you accepted something as good, but in reality, it is bad. And, PFR, probability of false reject, is probability that you considered something that is bad, and in reality, that is good. And both have cost associated with that, because when you pass something off as good, you're using that equipment to make other decisions that can impact people's lives, safety, health related issues, all kind of things. And or when you reject something thinking it is bad, you're spending a lot of money trying to figure out what's wrong when there's nothing wrong associated with that. And these tools that are in this document, they're there to help us save money, whether we're the supplier of measurement services, or whether we're the consumer of measurement services. And I say measurement services because I deal with calibration and testing labs. And, they both provide a measurement, whether it's related to calibration and testing in that way. And something you mentioned, Henry, so this document, it's not a completely like a starter document, but you can read it and then start as it comes up with I call 50,000 level concepts, and then it digs deeper into the detail. So you could start off with that 50,000 feet overview level of these concepts, and then it starts digging into a much more detail in a much more simplified way than the documents that Henry mentioned, like the JCGM 106 or, ILAC G8. Those are very good documents.
Excellent.
But the problem with that document is they assume some level of understanding because it is written by folks that think that you should have that understanding. And what happens in our industry or any industry right now, it is very hard to hire in people with that level of skill, some basic minimum skills. So laboratories end up hiring somebody with a potential to learn. And so when they don't have that basic minimum level, it's nice to have this kind of document to help them self-train or, train through places like sign calibration and so on, that they have a nice document to work with.
And we cover it all. I mean, we cover from definitions, measurement risk. We try to simplify as much as we can. We cover from the quality side of things. We show a stool with, five different levels, understanding the right requirements, purchasing the right equipment's covered, having the right process, which all these were covered by Greg earlier in his example, check your work, and then the continuous improvement aspect is of it, and that's the overview. And some people have said, "Hey, why not just go right for decision rules?" Is because what Dilip said, we don't know who's reading this. We want it to be a more complete document where you don't have to know everything about measurement uncertainty to pick this up. You don't have to know everything about quality processes. You don't have to know about CPK. But we're basically assuming that we are giving you that large overview, that and any of these topics that are of interest, you can read so many different books on things. And we added more. Dilip's adding the purchase order requirements of how you request that you get a decision rule if the lab's out there and doesn't know that. Greg's adding guard banding methods, and we have examples in here. I did a load cell example. Greg's adding a scale example. So there's very practical things that you're not going to find in JCGM 106 or in the other documents. Another great document is UCAS LAB 48. They when we started making this document, I know Greg and I were back and forth a lot, and then Dilip came in. Just trying to figure out what these documents were saying was very difficult, because you could extract a little piece, and Greg, talk about that. You extract a little piece from one, and then another one will get you further, and you combine like three of them to figure out what you did for the math part of it. So.
Right. So I'll give you an example of that. So in JCGM 106 and in Lab 48, I think they both cover an example of a guarded rejection. In a guarded rejection, they use the example of you're speeding, the officer's got a radar gun, and you want to be 99% certain that you're going to prosecute this person for speeding, taking into account the error of the radar gun. Well, one of the things that I was struggling with, because I like to see a closed loop. So in statistics, if I'm putting in a percentage, I want to see a Z factor, and then I want to take that Z factor and go back to the percentage to make sure that I ended up with exactly where I started. Well, in the case of the radar gun, by using a guarded rejection, it turned out math-wise that if the speed limit was 100 kilometers an hour and the car was doing 106.5 things like that, then there was a 99% probability that they were indeed speeding and you could prosecute them. Well, that's great. But I wanted to take that value of 106.5 and plug that back into the statistic equation and make sure that if it is 106.5, is it truly 99% probability? And the struggle that I had with that is that they were only considering the uncertainty of the radar gun itself, which in this example was 2%. So you have to take the 106.5 value that you recorded times the 2% of the accuracy of the radar gun. That was not clear in the example because I was trying to make a complete circle with, okay, you started here, this is what the answer is, but now I got the answer and I want to work back to the original question, and I couldn't do it. Because there was that little bit of piece that was missing that they weren't telling you, okay, you have to take the 106.5 kilometers per hour and multiply that as your measured or your mean value to get back to the 99%. So there was a lot of that. And I mean, I struggled with that. And that was a very, very simple example. In the document that we provided, that we are going to provide, that example is in there with the additional explanation of how to go towards it to make sure that you have solved for that. And a lot of the examples that I'm using in there as well, I'm going back to, okay, I said this is what I'm going to, this is the risk I want. These are what my guard bands need to be. If my measured value is at that particular level, then I should be able to work backwards and say, yep, that's what it is. And that's my level of risk. And I can see that and I can go backwards. So that's what we've done in this document to prove all of that out. So when the reader's reading that, they're not just applying it blindly, but they're seeing the proof of how it works and the inverse proof, which is very important. Another topic that we covered in here also is end of period reliability. Most folks have the assumption that end of period reliability is how many calibrations on this instrument did you perform and how many were in tolerance. If you perform 10 and one of them failed, then it's divided by 10, so it's 90% end of period reliability. That's what most people assume. That's a wrong assumption. The reason it's a wrong assumption is that's exactly the same thing as you're trying to measure 1 volt DC that has a plus or minus 0.1 volt specification. If you measure some value that's outside of 1, okay, fine, but you still have the uncertainty of that measurement that surrounds that measured value. So with regards to period reliability, what we're doing is we're taking that end of period reliability value and how many samples you've taken and creating a tolerance around your reliability. So when you're making a measurement in metrology, the question is, well, is my measurement in or out of tolerance and what's the uncertainty? When we're talking about end of period reliability, the question becomes, my end of period reliability is 90% and nominal, and this is my uncertainty about my reliability. So we're giving you tools in that document to be able to calculate that as well, which is something that I don't think most understand, that there is a tolerance around your reliability. It's there, but you don't realize it until you have the tools to be able to look at that.
And I think many overlooked that, Greg, because that was one of the things that all three of us were you talk about risk levels, specific risk and global risk, and for the listeners, they may not know what these are. And where specific risk, you can kind of think of in instantaneous liability. We're measuring something, we're looking at it immediately, and we're basically taking the measurement uncertainty directly into account, right? And then that's going to set our acceptance limit, which our acceptance limit is the tolerance limits minus the guard band. So if we're going at it that way, specific risk is one that not everybody uses, but it makes a lot of sense just to say, hey, did the basket, I use analogies, hey, did the basket go in or not, right? Do we have a pass or not? Global risk, right, uses more on averages, where what Greg's talking about of end of period reliability really comes into play. And some of these documents don't explain it very well. And either one of you can take over from here if you want to keep for the listeners to give them a summary of it, or I can. It doesn't matter.
Well, the other way you could look at it is when a calibration lab gets a customer's device, they're making a decision based on one measurement on a specific data point. So that's your specific risk in that way. Mm-hmm. But if I have my standard that I have, and I have a lot of history associated with that, then I'm going to make a decision based on the global risk.
You can.
Yeah. So because I have a lot of history associated with that. A customer's device, I got to make a decision because I can't keep the customer's device forever. And the other thing is that part of that is because I just have that for the short term, I need to have standards that are really good with very small uncertainties. So I have confidence in that measurement. And that's some of the things that Henry talks about, having lower uncertainties. Mm-hmm. Greg talked about his example earlier when he was dealing with that client that just buying the better equipment. Now he was dealing with a company that produces the product. So again, it's the same kind of thing where the product they make, they don't have time to test that product for 6 months. It is in a production process and it has to go out. So having the better equipment definitely, helps make that decision with much better confidence when you have lower uncertainties.
And I just want to add to that too, what I mentioned about end of period reliability and the tolerance around your reliability. So that plays into global risk, because the more samples that you have, what ends up happening is, yes, your reliability increases, but that tolerance that may have started out like this, and I'm looking at my spreadsheet now for my example, I want 89% end of period reliability, 95% confidence. That means I need a minimum of 26 sample sizes just to demonstrate that that's where I'm at. So in the example that I brought up earlier, I have 10 calibrations and 9 of them passed. Yes, that's 90% end of period reliability as a nominal. But when you do the math, and you want to be conservative, the true reliability is somewhere between 99.75 and 60.6. So to be conservative, you would say that your end of period reliability, because you have very small sample size, is 60% EOPR. Now, as you build up more and more sample sizes, so if I made this by a factor of 10, let's say, so I have 100 tests and I have 90 that were in tolerance, keeping everything else the same. Well, now my end of period reliability is 83%. So my true reliability is someplace between 95 and 83%. So to err on the side of caution, it's going to be 83% is what I'm going to err by. And if I have 26, which is the minimum number that I need, and all 26 passed, then my end of period reliability of my lower calculated confidence bound is 89%, and I am there. But that's something that is a new concept to probably a lot of the listeners. And
they're probably confused because you're running a lot of math. So,
well, one thing I wanted to throw in there where this really sneaks in for the everyday average person listening is, especially those, I should say, going on site, right? Because I could go to, every day that I go to an on-site appointment, I could have 10 things that are scheduled and then 5 things thrown in, right? Like as I get on site, 5 other things thrown in. And sometimes you don't have a lot of information on them. And you're sitting there trying to negotiate with the person, your contact that you might have a really good rapport with, like, what do you need this tested to? And I think a lot of times people just, because of convenience, because of just perceived simplicity, they say simple acceptance. I mean, what's the tolerance you need, right? Like that is so common in the industry today. And I think that's why it's important that we switch some focus to the decision rules, because I know I was never a part of contract negotiation or any of that when we're sitting there in the lab, right? But then when you're out, sometimes in other places, that will creep in, and there are people doing tests that probably are not not appropriate for the risk there. Like always,
Sure.
I use this oftentimes, sterilization, right? They need a strict 1/2 degree tolerance, but we all know your own device could be biased one way or another. And if you don't put some analysis into that, you could be giving a really bad cal just because you're trying to help out. Right, just trying to help out the customer. So I just wanted to throw that in there as well.
No, love that. And the other analogy we've all used, I think, is you wouldn't use a ruler to calibrate a gauge block. I think that's something everybody can understand. But if you're not taking measurement uncertainty into account, there's nothing really to say that someone's not coming out with a device with the equivalent uncertainty of the ruler to try to say your gauge block is good or not, which is absolutely ludicrous, right? We think it doesn't happen, yet it does. We walk into a lab and you see torque. We do a lot of torque. You see a worn square drive, and it's like, okay, that has a huge impact on the measurement result. Yet, are you factoring this in? There's a lot of hidden stuff, but I did want to say, to just simplify things, hopefully a little bit, and these guys can correct me. There's an example. I use different examples, but the one I like the most is Steph Curry. If people haven't seen, he takes like all these shots, 3-pointers, and makes a ton of them. So if we're looking at specific risk and Steph Curry shooting the ball, it's, did the basket go in or not, right? Is it between the rim? That ball, did it sink between the rim? If it did, it was good. On global risk, Greg was talking about EOPR, you say, wow, Steph makes 97 of 100 shots. Those 3 that didn't go in, if we use the law of averages, they're actually in. And I think that's where it depends on your risk tolerance here on what you want, because global is using averages, right? We're using large sample sets. Doesn't mean it's right or wrong. And the basketball analogy may not always, it may not capture it, but specific risk captures that immediately. Did it go in or did it not? Global says, hey, we know a lot more about our process, that even though that we're measuring and it's out, we have enough data behind it to say, even though on specific it's out, we really think it's in globally. And you want to add anyone want to add to that?
The one thing that Ryan mentioned about going on site, a lot of times when you go on site and let's say you're calibrating 10 multimeters, same make and model, but how the customer, the end user, is using those 10 multimeters, 7 of them could be used by an electrician just to check if there's line voltage or not. And 3 of them could be used in the production to make critical electrical measurements. But you, as a supplier of calibration services, don't know. You just have 10 multimeters, same make and model. Okay, so now the dilemma is, what is the requirement, the specification? Do you need the same specification for all the 10 meters or not? And you as a supplier, a calibration lab, are never going to know that information easily. But at the same time, you want to do a good job and calibrate them properly. And the best thing you could do is have a standard with the best uncertainty, and most likely, you're going to calibrate it, which is pretty typical, is to manufacturer specifications, however tight or loose they may be. Because if those meters were from Harbor Freight versus a meter from a well-known, reputable manufacturer, that could have a lot of impact on all those things. So it makes the making the conformance decisions difficult in that way. And having these tools at least helps you as a supplier of calibration services make the best decision with the best confidence you have. And then if you're a consumer of calibration services, again, you can use the tools to determine, did I really get a good calibration or not?
Just a quick piggyback off that. Those of you listening out there that do on-site stuff, it is okay to say no. If you don't have, especially, I know I've worked at labs where they don't want you to travel with the SPRT, right? So they might have to work out something different, a different arrangement. If the measurement scenario is not appropriate, you might have to work something else out. Sorry, Greg, go ahead.
Well, I was going to say to Dilip's point about how, you calibrate everything to the manufacturer spec in terms of the best that it can possibly be. There is caveats to that. If you know your customer and you're taking precautions, I'll say that this name because the company no longer exists, but I worked for Ford Aerospace in Newport Beach many years ago. And a lot of the tech equipment that was utilized in engineering was not calibrated. And we had special stickers on it that said not for quantitative measurements. It wasn't calibrated. The reason being, you have, at the time, an 800 megahertz scope or whatever it may be. And how could that not be calibrated? Well, it's because the engineers were looking for a specific pulse width. It had to look a certain way. The RI may not be that critical. We're looking for signals at certain points. They didn't need anything that specific. So in those particular cases, we didn't bother calibrating it because it didn't matter, because everything in those use cases, it didn't matter. You're just checking, to your point, Dilip, maybe you're using the meter to check for line voltage. And in this case, it was the same thing, to where they were simply checking for a waveform. Does the waveform look like this? Yep, sure does. Yeah. It's about that amplitude. Good to go. Don't really need quantitative data on that. Just need to make sure that it's there. So we were able to trim a lot of money off of our calibration O&M budgets by being able to do that, and being able to say, okay, this giant group of equipment right here doesn't need periodic recall because it's for R&D purposes, not necessary. On the flip side of that, I had an engineer come to the laboratory and gave me a microwave attenuator set, and he said that it's broken and I need to fix it. And I'm like, oh, I don't fix microwave attenuators, but what seems to be the problem? And he said, well, you see the sticker right here, it's broken. And I'm looking at the sticker. I'm thinking he's going to say the cal void. No, he was talking about the cal label. And I said, oh, you need a new calibration. He goes, no, I just need a new label on it. The label's broken. I go, no, the label is expired. You need a new calibration. And I have to send these over to our primary lab to be able to do that. And he was just like, well, no, let me show you how I use these. And he's explaining, I'm like, you're using them for microwave attenuation. What are you building? And he was building something to do with the HARM missiles. And I'm like, no, you need those calibrated. But there are people that do that too. So it's just, you really have to know what's going on and how this stuff is used. And, then you can apply some risk models to it. But man, I've seen a spectrum of things, as of you, Dilip, and you too, Henry.
Yeah. And in this case, you were a more informed consumer. But in the case where at a large company, everything goes to through a purchasing, And to them, a meter that's used to check line voltages or one to make critical measurements in a production process, it's the same thing. And so that's the kind of differentiator where if you're an informed consumer, that is really great. Or you have a calibration department that everybody comes to, and like what you said in your example, Greg, in your previous place of employment, that is great. But a lot of times
No, you
we
don't.
don't have that, and then that's a dilemma for the calibration supplier. Yeah, what do I give you?
Right.
Yeah.
It's a big dilemma for the consumer too, because we do we've all heard the horror stories. One of my favorite ones is pull 10 pieces and we need 10 to pass. And then someone pulls 10 pieces, 5 fail. Go pull another 5, 3 fail. Go pull another 3. And they end up pulling 25 to 30 samples for 10 to pass. And they think nothing of the 15 to 20 that failed during that process. And now we're good to go. And you actually, as silly as that is, you actually have that going and just we're talking about decision rules, but it really accounts for everything. I mean, we have examples of risk scenarios where a company messes up and bad things happen. The film Deepwater Horizon is one of the best films out there with one of my favorite actors, Kurt Russell, in it, where it talks about the blowout where it killed 11 people and just basically destroyed the Gulf that's dealing with red tide and everything else. Then you have a Texas refinery that blows up from calibration equipment. And you have Paul was on, you talk about the Hubble telescope. That was a calibration blunder. We talked about the Spirit of Kansas, another calibration blunder. That one wasn't really a risk. Well, that was risk on another thing with the process. Though there's recent ones with phones and batteries and stuff. So if you fail to buy the right equipment with the proper measurement uncertainties, establish metrological traceability, and employ the right decision rule for what you're doing, bad things will happen. And I don't think any of us want to fly on an airplane where we have these quality concerns, where Greg was talking about end of period reliability. It's 66% chance that it's okay by your math, but someone's claiming it's 99. There's a big difference in that gap from 66 to 99. So, but yeah. I mean, there's so many examples of this, and this is where our passion really comes out. The three of us is we just want to put something out there that's going to help. It's not perfect by any means. I don't think anything anybody ever does is perfect, and it can always be improved. And we're probably going to have multiple revisions of this document as people get their hands on it and say it would be nice to have this or that. Someone said it would be nice if you broke it up into several different things for different audiences, and we're like, no, we don't want to do that. We want it to stay like this global document for these purposes, from the pretty much the novice that has some experience, not a day one on the job, but from the novice that has some experience to like someone that's seasoned. I mean, Greg probably would have loved to have this document 2 years ago, and then he wouldn't have had to do all this math and spend the hundreds of hours he spent coding and doing it. He could have been doing something else. I don't know what that would have been, Greg. Would
Yeah.
Go ahead, Bill. I'm sorry.
When we started working on this document, I mean, we think about it, we already have roughly 10 revisions. First, between just the three of us, we had several. And then the document was put out in the public, and we had some really good feedback. And like Henry said, that, we will always look at and, come out with things, improvement, additions, and make it more clear as we get the feedback.
So, Henry, I just wanted to piggyback on what you said about you're pulling 10 samples and they pass, well, no, 5 fail. This is true. So when I worked at Ford Aerospace, they had a production system that tested the Sidewinder seeker heads. So what their process was is they had what was called a hanger queen, and a hanger queen is a known good Cenker head. It was allegedly as close to nominal as it was. So the premise was you install the hanger queen in the test setup, and if it passed, then you ran product all day long, and you had failures as you ran the product, and you had passes as you ran the product. When you put the hanger queen back on at the end of your shift, then that was your check that the stuff that you failed was truly failed and the stuff that you passed truly passed. Well, the problem was I had about a 60% failure rate on stray light testing, meaning when you're testing the sidewinders, for those watching this, they utilize an IR heat source with an autocollimating mirror to simulate distances with an aperture. So what has happening is as the sidewinder is locked onto that IR heat source, they have another box that simulates dropping flares to make sure that that missile doesn't go flying off and chasing a flare. Well, that's where all these seekers were failing the test. Well, over 50% of them were. And I got told by quality engineering, no, you don't understand. You just test them again. They'll pass. There's a glitch in the system. And I'm like, wait a second, you're telling me that I have to keep running these until they pass. And that's not giving me a whole lot of confidence here, but that stuff happened. And this was back in the late 80s. So, I mean,
what's the definition of insanity again?
Oh my gosh. Yeah.
So I have an anecdotal story. Back in the 80s where, this quality movement was starting again. And IBM was making those printers, and the stepper motors for the printers they were ordering from their Japanese supplier. And their requirement was they will accept 2% failure rate with those motors. So when they got the supply of motors, they were boxed in, 100 quantity. And when they opened the box, there was a note and say, oh, here are the 100 motors. These two marked are defective. We don't know why you want 2% failure rate, but here it is. So every box of 100 had 2 defective ones. So they met the requirement exactly 2% failure rate.
It was nice they marked them so they didn't have to catch all 100. Instead of saying, hey, we gave you 100, but we know 2 are bad. Have fun.
They just didn't understand why somebody would want not all 100 properly functioning.
Yeah.
Right.
But there was that, cultural kind of thing. But I thought it was always funny.
These things happen, and continue. There's other things that people can do that are listening out there. You bought something, you might have bought something better, or the manufacturer spec'd it too high, or spec'd it higher than what you actually need. And if you wanted to, Greg touched on like end of period reliability, but if you wanted to increase that, you might say, hey, I only need this, like our temperature probe, I only need this to be good to X. And you could tell the Cal Lab that instead of just blanketly saying manufacturer specifications, you'd say, hey, I really bought this device that's 0.01. I only need it to be 0.02. So maybe build in your own decision rule and say, all right, let's go with an 0.15, an 0.16, do the calculations, which our document helps you figure out how to do, and tell them where you want it to pass or fail. This is where we don't see a lot of purchase orders, and using the last minutes that we have on this is very few people. They give you blanket statements, and I don't think they understand them. Some may. So there are some out there. We all know the famous 4-to-1 TUR, 4-to-1 TR. We all know those famous statements that are put on some purchase orders, and some may understand that is a way. If they're using TUR, if they're using that for global risk, they may understand everything. But others may just have heard it somewhere and they're just blindly putting this stuff on here. So if you're doing that, this document's going to help you understand what that means. What does that 4-to-1 TUR mean? And on the global risk, it is funny how close that is if you're looking to get better than 2%. No matter what your end of period reliability is, if the lab calibrating your standard and you're okay with global risk has a 4.6 to 1 TUR, or measurement capability index, we should use better terms because TUR is often butchered and defined everywhere differently. then the risk would be controlled to 2%. Greg, do you want to add anything to that?
Yeah. So that work was pretty much done by Michael Dobert, and it was also confirmed by several people: Scott Mims, Paul Rees, John Harbin.
Mm-hmm.
So how that kind of came to be is they discovered that if you took all aspects of end of period reliability of both the unit under test and your device under test, there is no point in time where your PFA would ever get above, I want to say 15%, but it was 14 point something. So what they did is they modeled this mathematical model that took those two integrals, put them together, and took the worst case, which turns out to be about 62% end of period reliability, and apply that math to the model. So it doesn't matter where you are. If you're less than 4.6 to 1 and you use this method 6, you're always going to have a 2% risk. So when Scott Mims did his work with NASA, Henry and I sat down with Scott for, what was it, Henry, almost a week, right?
Yeah,
Yeah, we sat down with him for almost a week, and the in a nutshell, Jerry Hayes came out with a paper in 1955, and really talking about test certainty ratios, but somehow test accuracy ratios got in there. But he said that, if it's at least 4 to 1, that you should have a 2% risk. Well, he was off just a little bit. If it would have said 4.6 to 1, then that would have tied it together. But utilizing the global model, the Dober method, that does keep your risk to 2%. So the calculations and the code that we've included in this document allows you to modify that somewhat if your customer wants, let's just say they wanted a 1% PFA, and you have enough information to use it globally, you could utilize that function to reduce that PFA even more. And should be noted too that a decrease in PFA is an increase in PFR. So
lots of rework.
Yep. So the tighter you want to make your decision about, I don't want to accept anything that's I don't want to pass along anything that's bad thinking it's good. The smaller that number is, then the more rework you're going to have on the other end. They're inversely proportional.
Right. Yeah. So there's a good balance to that, so economically viable balance that you have to kind of make a judgment.
Right.
I always say, if you don't know, one of our arguments is, if you don't know, buy better equipment, right?
Right.
If you haven't done your analysis, you're probably not going to get bit by buying better equipment. It's the safer, of all things considered, it's the safer thing to do as far as rework your PFA, probability of false accept, and your probability of false rejects. Passing something that's saying it's conforming when it's non-conforming. We'll use those words too we haven't been using the other words. And that's one thing that these documents do. They interchange words. So today we've been saying something that is good when it's bad, but in a lot of the documents, it's conforming, non-conforming. You just have different terminologies all over the place on these, on just TURs all over the place. And that's why we should talk measurement capability index. But before, I know Dilip has something here, though. There's nothing that stops, as I said before, there's nothing that stops you from raising the tolerance. You don't always have to go with manufacturer's tolerances. If you need something, if you don't need that, there's nothing that says, hey, like let's just raise them. There's going to be a much higher percentage that you're going to be in. So many people get clued in to, just calibrate to manufacturer's specifications on one end when they don't need it. And the other end of things is they buy something that's junky, and then they expect it to be great, and they don't understand why it keeps failing all the time. And that's the other end of the equation. That's a harder end, because when people buy the wrong equipment, they tend not to want to fall on the sword, and they tend to double down. A lot of people in quality have this it's the guy drowning again scenario, guy or gal drowning that are silent. They don't scream out for help. And
Right.
I blame organizations on that one, and cultures of organizations, because if you purchase something, made a mistake, and you're going to allow the organization to lose $1 million over the next year because of bad equipment versus just fessing up and saying it's going to be $20,000 to correct this situation, and we won't burn that additional, $1 million. That's really where we are.
Yeah. So one comment I want to make is we're covering part of the equipment issues here,
Mhm.
but then the implementation of that equipment in a process is a whole wide, open world where you could buy the best equipment, use it in the wrong process, or you could buy the worst equipment and use it in the right process, or you match the right equipment to the right process. And then you got to deal with all the process production, variables, and then come up with a good product, whatever that product is. It could be a tangible product, or it could be your service, the calibration report, which is also a product.
Could be a Dilip bobblehead, though. Who's making them?
I don't think they're going to sell very well.
I don't know. You might be surprised.
So I think you'll be hanging out at the conferences signing those things, Dilip.
That's what I'm saying. That's a collector's item. So what's this podcast releasing on the week of the 15th? Is that close to when the final document will be, or is there still time for people to give feedback? How is that all working, Henry?
Yeah. So the people that are listening, this document is out. You can go grab it. We're happy with it. As I said, it's not perfect by any means. It's going to simplify things a lot. The current feedback that I've gotten, we've sent it out to about 100 people, and the best feedback we've gotten is either we think you should do this, which we've implemented almost immediately. Some stuff like you didn't capitalize an I here or this, but the best feedback is, wow, we are now looking at our processes and how we're going to implement this because you've simplified it for us. And that is really what our aim was to do, to make something that seems like this huge daunting task to people that do not understand how to do it because they've always done something a certain way, and make it pretty simple. Right now, Greg's global risk stuff with the integrals and stuff, the math's there. You can implement it. That still, to me, is not super simple, but the specific risk stuff is just a couple Excel formulas that you can just copy and paste, throw in there, and get it immediately. Those sections go over the graphs and what risk is, and there's some bits on measurement uncertainty. And I did say that about Greg's global risk, the stuff that he did. Though, if you're close on that, this is going to push you over to be able to implement. But if you've never done anything before, chances are you're probably going to start going with some specific risk models, build up all of that information, right? All of that data. So of like instruments, and then you can build up to going towards a more global approach. And with that, Greg, do you want to add to that?
Yeah, and one of the things I want to add to make on the specific risk side of it. So another thing that I've seen as well, and I'm talking on specific risk, not global in this sense, but on specific risk. Let's just say, for example, you have a client that wants a 2% specific risk on whatever process it is. When you take your best measurement test equipment that you have and try to perform this calibration, even if you're sitting at nominal, already at 5% risk without even moving the needle. So how do you reach that 2% risk that the client is requesting. Well, we give you some very simple tools in there on the specific risk side. So I think most listeners know what a limited calibration is, but I've never seen it documented into the sense of, okay, we can't meet this spec, we're going to make it a little bit wider. Well, how much wider does that need to be, and what's the rule of thumb of doing that? Well, instead of using some rule of thumb, what we're doing is saying that if you want this level of risk, and this is what your uncertainty is, and this is what you the max risk tolerance that you can take, what it does is it takes your acceptance limits, puts them outside your tolerance limits, makes the tolerance limits now the actual guard band. So now you've got a limited calibration, does have the bandwidth that is needed to be able to meet that client's risk. As long as the client is okay with what you're doing, we're giving you the tools to be able to do that and give you a mathematical reason to make them X wide. Instead of just saying, well, it can't meet this tolerance, so I'm just going to increase the tolerance by 10% and call it good.
Arbitrary.
No, actually, we're going to extend tolerance into a statistical tolerance that will enable you to reach that level of risk that you're comfortable with.
That's really cool.
And satisfy the contract, the contractual agreements. So,
right.
But yeah, we are super excited about this.
Yeah, so one advice I give every time, like I teach a class and I share tools, is go play with it. You're not going to break anything when you're doing the things in Excel, but play with the what if scenarios. Copy and paste the Visual Basic code that Greg has and play with it.
Right.
Yep. You're not going to break anything. You just, if nothing, all you got to do is, delete the spreadsheet file and work with it again. And the more you practice with it, the more your understanding will be. And that's the whole idea. And then that's going to make you a knowledgeable user of how to implement the decision rules.
Right, and that's what we encourage everybody to do, is to, like Dilip said, take the information, take the code, put it in a spreadsheet, play with it, get familiar with it, understand how these functions work, what they mean, what they're telling you, to get familiar with it, because a lot of stuff has been siloed, like I said, for years, if not decades, because I've been asking for the formulas and the code to get global risk for a long time. And for the most part, I've gotten either stonewalled or I got a cryptic answer that is like, all right, I need a PhD in mathematics to understand what you just did here. So over the years, I figured out this went, why I'm like, all right, there's no reason anybody else has to go through what I personally went through in my personal quest to understand how these things work. So that was part of it too. It's like, all right, I know how to do it. Here you go. So take these equations, take these instruction sets, see how you can apply them to your organization, because I think I could speak for everybody here. We all like flying on airplanes that don't crash, and you like things to be accurate, and you certainly want your cell phone and GPS to work the way it's supposed to work. And if you have an implantable cardio inverter defibrillator in your chest, you want to make sure that works.
Pretty much, yeah.
And
you go ahead.
And one of the things I want to say, the three of us like to work together because we have the same philosophy, share whatever we develop so somebody else doesn't have to reinvent the wheel. And my philosophy always been, the more you give, the more you get. And so that's why and that's the same philosophy both Henry and Greg have, and that's why it's a pleasure working on this, document.
Well, that's perfect, because I was going to, just for a brief moment, speak on behalf of the industry and say thank you to the three of you for the work that you do on this, and for the contributions and advice for everyone going forward, because I know it's very time consuming, to put this type of stuff together. One before we have to go, one quick rapid fire question for all of you. We'll start with Henry. Best Kurt Russell movie.
Oh my! I should go with it's rapid fire, and I have to pick Big Trouble in Little China. I have to pick.
Good one.
I can't not. I have so many though.
Okay, Greg.
Kurt Russell movie. Toss up between the Christmas Chronicles and Bone Tomahawk.
Oh wow, yeah, those are good. Okay,
dig into the obscure Bone Tomahawk, are we?
Yeah.
You're not going with the strongest man in the world, the Disney movie. You're not going with the Fox and the Hound. Come on,
I'm going with that one.
Dilip, you a Kurt Russell fan? You got a favorite?
Oh my God, yeah, I would have to say it's been a while since, but Big Trouble in Little China, is that the right title? Yeah,
that is. That's the mine, and
that was a fun movie.
But my wife likes Overboard, and I must second that is also a great comedy. As Captain Ron is another one if you haven't.
But talking about movies, I watched Oppenheimer last year, and I really loved that movie because it has got so much historical significance for us, and so that's one I would definitely recommend. I really enjoyed it.
Those math calculations are probably a little more difficult than global risk, but
yes.
I love the line. I love the line in that movie where it was like, well, the probability is close to zero.
Yeah.
Destroying the entire planet. Yeah.
Yeah, that was a great line. And the other line was, Oppenheimer says, I'm going to show Einstein these calculations. And he shows those calculations. Einstein just takes a glance at it. And remember, we're in the BC days, before computer days.
Right.
And he looks at it and says, yeah, they're right. I mean, how smart can you be when you can just look at this and say, yeah, these are right?
Those are the people that do not need to read this document. They probably can easily dissect the other documents. For the rest of the population, this document will be available from MH Force's website for sure. We're going to post it. I think Ryan's posting it.
If you're in the school, it'll be in there.
It'll be in the school. LinkedIn. If you follow us on LinkedIn, follow the companies on you'll have announcements. And our hope is to get a working Excel spreadsheet to people. We're not going to commit to a timeline on that. We have some things in development to go with this, but we want to put this one out for you to play with, you develop, learn from, learn norm disk functions, S inverse, all of the cool thing in this. And I'm very disappointed in this group that no one mentioned the Snake Plissken movies. So I'm going to have to bring them up, that Kurt Russell was Snake Plissken and Escape from New York and Escape from LA.
Well, I was going to end it with saying thank you all, and the correct answer is Tombstone. So,
oh yeah,
yeah,
that's right.
Once again, thank you all, and for the hard work on this stuff and the contributions that you all do. So thank you.
We're happy to spend our 15 minutes that it took to create this document and help
it was fun to work. It was fun to work on it.
Yeah, hundreds of hours between us. So hopefully the community will benefit.
Check out the document, and thank you all for listening.